Okay, so two bits of news. I'll have your tests back on Wednesday. I don't have them today. And then I said we were going to have a quiz on Wednesday, but I forgot to make the one for dynamics, and so that's postponed. Um, but I'll let you know ahead of time um, when we're going to have it. Uh, okay, we didn't have an assignment last class, so Um, let me just sort of refresh your memory about what we're talking about. Um, so where we are. Um, we talked about internal loads, and we're getting into using internal loads in beams. To calculate stresses. And we're doing that by using the idea that the total stress tensor at a point in a beam is equal to the stress tensor produced by tension compression at that point, plus the stress tensor produced by bending moment, plus the stress tensor produced by shear force, plus the stress tensor produced by torque. Okay. And so we're just going through these one by one. We've already talked about calculating the stress tensor due to internal tension compression. Oh, before I go into that, anybody remember what the principle is called that allows us to approximate this total stress as the sum of the individual stresses? Yes, very good. Superposition principle. Um, and it's not uh, like rigorously true, but it's very close to true in cases like ours where the deformations are small. Okay, so for tension compression, I mentioned before that one of the things that's important to keep in mind as you work on these problems is the restrictions on the types of beams for each of these calculations. Anyone remember what the restrictions are for using internal tension and compression for calculating stress? Trick question, kind of. Actually, for tension compression, there's no restriction at all. Whoops. There we go. So no beam restrictions. You can always apply this. And it says that the XX normal stress is just equal to the internal tension divided by the cross-sectional area. And for all of these, you can trust the signs. So if you have a positive value for the internal tension, you get a positive value for sigma XX. And over here on the side, let me draw one more thing here. So let's say that this is our beam. Let's remind ourselves what coordinate system we're always using. Okay, so what are we calling the axis that's along the beam's long axis? What? X, right. And what are we calling the axis that's up? Y, and that means that from this view, Z would be coming straight out towards us. And a lot of times we're going to also want to think of the beam when we're looking straight down the right end, like this. And in that case, so our cross-section will look like this. And our x-axis would be this way, our y-axis would be this way, and our z would be to the left. Okay, so that's about all we have to say about tension compression. And now we're talking about, we've been talking about the stress due to the bending moment. Okay, there are 3 beam restrictions for using the bending moment formula that I'm giving you. So 3 beam restrictions. The first one is it has to be straight or nearly straight. The second one is it has to be prismatic or nearly prismatic. Anyone remember what prismatic means? Yeah, the cross sections stay the same as you move down the x-axis of the beam, down the long axis of the beam. And then the third one is the cross section has to be symmetric about the y-axis. Okay, so if those 3 things are met, we can calculate the stress at a point in a beam due to the bending moment as sigma xx is equal to negative bending moment, so that m is the internal bending moment, times y divided by I. And m is the internal bending moment, what we calculate from the internal loads calculation. Y is the height above the neutral axis. And I, anyone remember what I is?
Inertia.
Yeah, yep, it's the moment of inertia, but it's not the mass moment of inertia, it's the area moment of inertia. Yep. And we started talking about how to calculate that area moment of inertia. Let's see. Yes. So for the moment of inertia, I gave you the moment of inertia for 3 simple cross-sectional shapes. The first one was a rectangle. So remember that these are cross-sectional shapes. The neutral axis goes through the centroid for all of these. So there's the neutral axis. And if this is the height h, and this is the base b, then the moment of inertia is 1/12 times the base times the height cubed. And if you remember, I said it's it's an important feature of this calculation that the height is cubed and the base is linear. Um, remember that to avoid this thing bending up or down, it's much more valuable to use your material to make it taller than it is to make it wider. And that makes sense if you think about like bending um, a piece of sheet metal or something. It's super easy to bend in one direction, very hard to bend if you flip it at 90 degrees and try to bend it uh, when the height is big. Okay. And then the second shape was a circular cross section. So there's the neutral axis. Um, and the radius we're going to call r. The moment of inertia is pi r to the fourth over 4. And then the last one was an isosceles triangle. It has to be isosceles because of the symmetry restriction. So the two diagonal legs have to be the same. The centroid would be something like this. So the neutral axis has to go through the centroid. Um, and again, I'll call this the base. And this the height. So I is equal to BH cubed over 36. All those formulas are for the shape's neutral axis. And the question then is, what if you want to calculate that moment of inertia for a different axis, not the shape's neutral axis? So what if you want I for an axis that's not the neutral axis? And we'll see why you would need that in a second. And the answer to that is the same as the answer for the mass moment of inertia in dynamics. Use the parallel axis theorem. And so the parallel axis theorem works like this. It's very similar to the mass moment of inertia one. So let's say that the centroid of or this is a cross section. All of this stuff, we're looking at cross sections. And let's say that the centroid of this blob is here. Then that means that the neutral axis goes through the centroid. And say that the axis that you want is this. So this is the desired axis. Um, So this is the desired axis. Let's call it A. Then the area moment of inertia about A is equal to the moment of inertia about the neutral axis plus this parallel axis theorem part is basically like if you were forced to guess what this was based on what you know from dynamics, you would guess that it was going to be, since this is area, not mass, this would be the area times the distance squared, where this is the distance, d, and that's what it is. So if you remember one of them, it's easy to remember the other one. This A is the area of the cross section. One thing I want you to notice here is area can't ever be negative, and distance squared can't ever be negative. So the smallest area moment of inertia you can have is the one that goes through the shape centroid. If you move it away from the neutral axis, it just gets bigger. Okay? Yep.
When we were doing centroids, we said that you could either add two shapes together to get the rough centroid or remove them to get what you wanted. Could that work with inertia where we remove the section?
Yes, it does work. Yep.
Wouldn't that mean you have like a negative area then?
Well, you would do it, let's see how you would do it. So don't write this down. I'm just going to, so if you wanted to calculate the area moment of inertia of this shape, okay, you could do it as the moment of inertia of the red shape and then subtract the moment of inertia of the green shape. That's how you would do it. Okay, so notice that the smallest area moment of inertia is the one through the centroid. If you move away from the shape centroid, it just gets bigger. Okay, so let me do an example.
Would that one be zero then?
What?
The area moment
No, it wouldn't be zero. It would be from these formulas.
Oh, I see.
And if it's a different cross section than one of these shapes, you could use the well, really you just Google the different shape, but you could also use the integral definition. Okay, so here's an example of why you would ever need to use this parallel axis theorem. So let's say you have a beam like this. So let's say this is the cross section. And we're talking about the beam like this. And that means that our coordinate system has the x-axis going that way, the y-axis, the z-axis going to the left, and the y-axis up. Although we're going to position the origin of this coordinate system at the neutral axis of this shape. And so we want to calculate the area moment of inertia for this beam. So the approach we're going to take is, now the neutral axis always goes through the centroid, right? So we're going to start by calculating the centroid of that T shape. Then we're going to break up this cross section into two different rectangles and calculate the moment of inertia of each of the rectangles about the centroid of the entire T shape, okay? And then we just add them together, okay? So our roadmap is like this. So first we're gonna find the centroid, and that's gonna tell us where to position the neutral axis. Then we're gonna break the cross section into rectangles 1 and 2. And we're going to calculate the area moment of inertia of 1 about the neutral axis. Let's see, how am I going to, let's not call this neutral axis. I'm going to call the neutral axis here, I'm going to say that's going to be our axis A. And we're going to calculate the area moment of inertia of rectangle 1 about A, and the area moment of inertia of 2 about A. And then finally, the total area moment of inertia about A is just the sum of those two. So this is the reason that we have to use the parallel axis theorem, because sometimes our cross sections are going to be made up of multiple simple shapes, and the neutral axis of the complicated built up shape is going to be different than the neutral axes of the individual simple shapes would be. You with me on that? Okay. So first step is I'm going to draw out this T shape. Oh, I didn't give any dimensions yet, did I? So let's say the dimensions are 0.5 meters. This is a huge beam. And then this is 1 centimeter, so 0.01. 0.01. And then this is 0.01.
So is 0.5 from the top, or is that just the bottom?
No, it's from the bottom. And then this is 0.5. Okay, so as an aside, this beam is huge. So how many kilograms would a beam like this be, say if it was 2 meters long? Okay, let's calculate that. So the volume, if it's 2 meters long, would be 2 times 0.5 times 0.01. That's the area. And then we're saying that it's 2 meters long. So that is 4 times 0.5 times 0.01. And then the density of steel is 7,000 kilograms per cubic meter. So
what's it 2 for?
It's 2 rectangles that have the same area. And then the last 2 is because I just arbitrarily said, let's say this beam is 2 meters long.
Oh, okay.
So multiply this total area by 7,000, and you get something that's 140 kilograms. So, 1,400 newtons. So this thing is really big. Okay, so let's calculate the centroid. So I'm going to call this rectangle 1 and this rectangle 2. And so for rectangle 1, the area is 0.5 times 0.01. So that's 0.005. And I have to choose a coordinate system for this. Let's put the coordinate system at the midpoint there, like this. Okay, so we can see that this is symmetric about where I put the y-axis. So we don't have to calculate an x location of the centroid. We just have to calculate a height of it. And so what I'm expecting to see here is a centroid that is just a little bit below my origin. So we're going to get a negative y value for the centroid of this whole shape. Are you with me on that? Okay, and according to this coordinate system, well, I'm only doing the y's. So the y centroid of rectangle 1 is, since the whole thing is a height of 0.01 and we are only going halfway up, this is going to be 0.005. Because the centroid, we want the y centroid location of that horizontal rectangle, and that is here. Okay. And then I'll go to rectangle 2. The area of that is the same, 0.005. This is 1, this is 2. The centroid location for rectangle 2, this time we have to go down half of the height of this rectangle, so that's going to be negative 0.25. You with me on that? And so the total centroid is 1 over the total area. A total is just the sum of the two areas, so that's 0.01. So we have 1 over 0.01 times the area of rectangle 1 times the centroid location plus the area of rectangle 2 times the centroid location of that one, negative 0.25. And I get a value of negative 0.1225. Okay, so if I redraw this shape now, I'm going to be a little more careful with dimensions. This is long and very slender. The centroid of this shape is this lower piece has a height of 0.5 meters, and we're going down, about a fifth of that from where these two are joined. So let's say the centroid is here. And that's where we're going to position the coordinate system. X is coming out towards us, Y is up, and Z is to the left. Okay? Are we done? No. We're just starting the moment of inertia part. So now we're going to do the moments of inertia. We just figured out where our axis is. So like this is our axis A. Okay, so I'm going to go to rectangle 1 again. That's that top horizontal rectangle. And I'm going to use the formula. So the moment of inertia about A is equal to, this is a rectangle, so I know we're going to use the formula that 1/12 times the area, which was 0.005, times the base. What's the base dimension of that horizontal rectangle? 0.5, yep. And then times the height cubed. What's the height of that rectangle?
0.
Yep. So 0.01 squared. Well, that's going to be a really small number because we're squaring that 0.01. But we're going to see that there's a pretty big contribution from the parallel axis theorem. So now I'm going to put in the parallel axis theorem part. We have an area of 0.05, sorry. And now we're going to take the squared distance from our axis A to the centroid of that horizontal rectangle. So that's 0.005 to get from the centroid to where the two rectangles are joined. You with me on that? And then another 0.1225. So that, I think, comes out to be 0.1275. Yeah. For what? Yeah, that's the parallel axis theorem. So that is this formula here. So we're taking the area and then multiplying it by the distance squared from the centroid of the shape to the neutral axis of the whole thing. So if I...
Centroid of the shape to the centroid of the whole thing.
Exactly. So...
Is that always positive?
Well, you could think of it as positive or negative, but we're squaring it, so it'll always end up being positive. Okay, so if this is our shape, and our centroid is here for the whole thing, and our centroid for just the shape is here, then this distance is 0.005. And this distance is 0.1225. And so the distance we want is from here to here, and that is 0.1225 plus 0.005. And yeah, that's 0.1275. And so if I put these all together, I got 8.1531 times 10 to the minus 5 meters to the fourth. And now we have to do the same thing for the second rectangle. So rectangle 2, so this is for rectangle 1. Now we're doing for rectangle 2. This is 1/12 times the area of rectangle 2, 0.005, times the base of rectangle 2. What's that?
0.01.
Yep. So 0.01 times the height squared. What's the height?
0.5.
Yep, 0.5 squared. And then we have to do the parallel axis theorem part. So that's the area of rectangle 2 times the distance squared. So what's the distance? How do we calculate the distance from the centroid of rectangle 2 to the centroid of the whole shape?
Like the center of the whole shape and subtract the.
Yeah, so it's gonna, you can think of it as like it would be from the centroid of that vertical rectangle, rectangle 2, it would be 0.25 to get to where they're joined. And then you have to backtrack 0.1225 to get to the point we want. So this is going to be 0.5 minus 0.1225. So that is 0.3775 squared.
50.25 minus.
Yes. Yes, it would. Thank you. 0.25 minus 0.1225. So this is 0.1275. That's the same as our distance from the other one. You know why that is? I mean, I'm just saying this because I didn't notice it before, and now I see I could have. Because they have the same area, so they have to have equal contributions to where the centroid of the whole thing is anyways. So 0.005, I'm multiplying this out.
So if the shapes have the same area, we don't have to calculate the distance.
It's just going to be it's going to be right at the midpoint between the two of them. I guess you still have to calculate it, but the distance is going to be the same for both of them. And for this one, I got 9.3781 times 10 to the minus 5. And so finally, the area moment of inertia of the whole thing is the sum of these two. And that is 1.753 times 10 to the minus 4 meters to the fourth. Okay. No, I did this. I plugged this formula in wrong. There's no area in this formula. It's just 1/12 times the base times the height cubed. So that won't take long to fix. Sorry about that.
What about the first rectangle? Did we include it?
Jeez. Okay. Okay. And this is not, and this should be cubed, not squared. Getting my formulas all mixed up. 0.5 times 0.01 cubed. 12 plus. And we get for this 8.132 times 10 to the minus 5. That one didn't change very much because the bigger contribution was the parallel axis theorem part. The other one's going to change a lot more. This is cubed here again. And so this one is 1.8544 times 10 to the minus 4th. And now add those two together. And you get 2.668 times 10 to the minus 4th. Because I have my notes from last year here. and I got a different number. And I was like, either this year or last year or both is wrong.
Well, I was gonna say something about that, like you multiplying the area, but I'm like,
Yeah.
I just missed something.
Yeah, sorry. I mean, I guess I was, who knows? The formulas get muddled. Okay, so now now we're going to use this and we're going to say, imagine that that is the beam we're dealing with. And we're going to imagine that it is a cantilever beam connected at the left. So let's say that this is, let's make the length 4 meters. And let's say that there is a 1500 Newton force applied like that. And then a point couple applied of 200 Newton meters. So if the beam cross section is the shape that we did above, we want to calculate the stress tensor at 3 different points. So we'll do it at the very top of the cross section. We'll do it at the neutral axis. And we'll do it at the very bottom of the cross section. Bless you.
You always do 3?
No, I mean, we could do any points we want. Yeah, I'm just asking this question, yeah. But what we're going to see here is how now locations on the cross section change what the stress is. Okay. So to do this, well, what's the first thing we have to do? We first have to calculate the internal loads of that beam. This is a pretty simple internal loads calculation. And we are going to neglect the weight, even though obviously the weight would be pretty substantial here. Can anyone tell me why I'm neglecting the weight in this problem? There's something about if we put the weight in there, there's something that we wouldn't be able to do yet. It would be a distributed load, which actually that's fine. But the problem is that that distributed load would cause a shear force, and we don't know how to calculate stresses due to shear force yet. And so the way I have it here, all we have is tension, compression, and then a bending moment inside. Okay. Okay, so first I have to calculate that external load at the wall. We have a counteracting force here, I'll call that R, and we have a couple here, I'll call that MR. Of course, you could put all the loads in a vertical load, but I'm just putting in the ones that counteract what we have. But you could do this with the exact same approach you always do internal loads. So Newton's second law says R minus 1500 is equal to 0. So R is equal to 1500. And then the moment equation, uh, the 200 is the couple. But for this, this is just Newton's second law, so we're only putting in the forces here. And now for the rotational one, there are no vertical forces. So the only moments are produced by these couples. So we have MR. Oh, I see, in my drawing. Yes, thank you. 200. So we have MR plus 200 is equal to 0. So MR is equal to negative 200. And now we can do a cut. We only need one cut here. So this is valid for the whole length of 4 meters. So x from 0 to 4 meters. We have a force of 1500 over here. We have a couple that's clockwise, or I could have drawn that counterclockwise and called it negative 200, but I drew it this way and I'm calling that positive 200. And then we have T, V, and M.
Don't get fancy T2.
Yeah, we could put that in. It's just going to end up being 0 because there are no torques about the x-axis in this problem.
Oh, yeah.
So we have a 1500 0 force plus T negative V. And so T is equal to negative 1500 and V is equal to 0. Does it make sense that that it's an internal compression if you look at what's happening in this problem? Yeah, that makes sense. So our internal compression of 1500, no shear force. And now we can go to the bending moment. And this is, rotational Newton's second law about the z-axis. We have a negative 200 plus m minus vx is equal to 0, but v is 0. So m is equal to 200 And so now we know that for every point along the length of this beam, the internal loads are the same. We have a compression of 1500 and a bending moment of positive 200. Okay, and now we're going to use those to calculate the stresses at these 3 points. So I didn't specify when I did this problem where along the beam we're looking, and that's because I set this problem up to have the same internal loads for every x value. But when that's not the case, you'll have to take the x position into account too. Okay, so now we'll start with the tension compression. Does this beam meet the requirements to use our formula for stress due to tension compression? Yeah, we didn't have any requirements, so this one always works. So our XX normal stress is equal to negative 1500 divided by the cross-sectional area, which was 0.01. And so we get negative, I'll write it as 0.15 times 10 to the 6 pascals. Are you with me on that? And so our stress tensor due to internal tension compression just has the XX value. Everything else is 0. So this is in megapascals. And now we'll go to the bending moment. Does this meet the beam requirements for the stress due to bending moment? So what are the beam requirements? The beam has to be straight, has to be prismatic, and it has to be symmetric about the y-axis. So does this T shape meet all those requirements? Yep, yep. So this meets the beam requirements. And so now our stress XX is equal to negative. The bending moment was 200. I'm going to leave it as Y for now, and we'll plug that in for each of the 3 cases. And then divided by the area moment of inertia that we got, 2.668 times 10 to the minus 4. And so this is 7.496 times 10 to the 5 times y, and this is negative. And now we just have to think about the points that we want. So for our point A, it's all the way at the top. Y, remember, is the height of the point you want above the neutral axis. So what's that going to be? Well, we know that the neutral axis, it's 0.1225 from the neutral axis to where the 2 rectangles are joined. And then it's another 0.01 to get to the top of the top rectangle. So this is going to be 0.1325.
Wouldn't it be another 0.005 to the top?
Well, I already did that. So instead of adding 0.005, I added 0.01. Yes, exactly. So 0.1325. So y is equal to positive 0.1325. And so sigma xx is equal to negative 0.0993 times 10 to the 6 pascals. And so the stress tensor due to bending is that in the negative 0.0993 and then zeros everywhere else. So the total stress tensor at this point is the stress tensor due to tension compression plus the stress tensor due to the bending moment. And so that is negative 0.15 minus 0.0993, or a stress tensor of negative 0.2493, zeros everywhere else, in megapascals. So that's at the top of the beam. Now we want to do at the neutral axis. This is point B. So what do we know about the stress due to the bending moment at the neutral axis? Like think of the meaning of the neutral axis. Well, I guess think about the formula.
Is it 0, right?
Yeah. If you think about the definition of that y that goes into this formula, where is it? Way up here. That y is the height above the neutral axis. So if you're doing it at the neutral axis, y is equal to 0. Okay. So at the neutral axis, y is equal to 0. So the stress due to the bending moment is just the 0 tensor.
Isn't that the total?
That formula was for the stress due to the bending moment. So for the stress due to tension compression, that one doesn't change as you go around the cross section. So we're just going to, when we do the total, this is just going to be the stress due to tension compression plus this 0 tensor. And so that is going to be negative 0.1500. But now something interesting is going to happen with this total stress tensor at the point C at the bottom. And that is that notice the, so now we're going to have a negative y value, which means we're going to have a positive XX stress due to the bending moment. So the stress tensor due to the bending moment is going to partially counteract the stress due to that tension compression. And so we're going to have a point at the bottom that's under less stress than if that bending moment wasn't there at all. Because the stress due to the tension compression and the stress due to the bending moment are in opposite directions. They offset each other. Okay. And this is something that you can use to your advantage in engineering applications by preloading. If you're worried about something breaking at a super point at some point, you can apply another load to it, preload it, so that when the load you're worried about comes in, your other load partially counteracts it. Okay, but let's see how this works. So point C. Okay, well, what were the dimensions? It was 0.5 to get up to where they were joined. And so from the neutral axis to the bottom is going to be 0.5 minus 0.1225. So our y here is negative 0.3775. And so our XX stress due to bending is negative of 200 times negative 0.3775 divided by 2.668 times 10 to the minus 4. And this time we're going to get a positive value. And this is 0.283 times 10 to the 6 pascals. And so now the total stress is the stress tensor due to tension compression plus the stress tensor due to bending moment. And that gives us positive 0.133 and then zeros everywhere else. So the point A at the top in this case was in compression. The neutral axis was in compression. But when you get down to the bottom of the shape, it was in tension. And the smallest absolute value of that stress was at the bottom, where the stress due to bending is in the opposite direction of the stress due to the compression. Any questions about that? Okay. Let's stop, and I'll give you a couple of problems like this to work on, but with less elaborate moments of inertia, I think. Okay, that's all.